Welcome. So on this lecture we would be covering about one of the super learning techniques, as I call them, and that's on decision trees. We would be following that with the next generation of learner called as random forest, and this is a couple lecture actually. Sort of you need to have it back to back. You will need all concepts of decision trees when we migrate over to random forests as well. So to start with, it's obviously not about jaywalking in a forest as you see over here, and it's actually all about these kind of structures what we are looking at, and each of them is actually called as a decision tree, and if you collate all of them together it's called as a decision forest, which is from the fact that a lot of trees actually make up a forest. So without much of an ado, how this is organized is I would be speaking a bit about the historical perspectives as what came first and how the whole field was evolving into decision trees and from then eventually to random forests. And then I would be speaking about how you build up your own decision tree. So this is where we do the math which goes behind creating them, which will be forming as the basis for us to move on next when we look into the coding stuff as to how can we actually get a problem solved with using these decision trees. So from there we move on to the random forest model, and then we discuss about some of the very engineering complexity perspectives, and one of them is the computational complexity, which everybody is obviously worried about, whether your say ubiquitous laptop can handle the same kind of a problem, or you need a very specialized hardware in terms of a high performance computing or a supercomputer to handle them. And the other factor is some of you might have been aware of a fact called as feature selection, which is quite common in the community in order to reduce down the feature set, or sometimes you also work on a stuff called as feature compression. So random forests and decision trees together, both of them have an inherent problem of eliminating useless features from them, and that's where we discuss about variable importance and how you can use that in order to speed up your whole algorithm development process. So coming down to the first part of it is on historical perspectives. So decision trees typically came up with these four famous people called as Bremen, Friedman, Olshan and Stone, and they wrote down a very famous book called as Classification and Regression Trees, which comes down also as an acronym called as CART, and you might have heard about this one long back. So this was a work which was funded by the US Naval Research Board somewhere in early 80s, and the book came out around 1984. And interestingly, this whole machine learning paradigm got developed for solving medical problems. So today you have clinical decision support systems. One of them is OncoSyn, there is SynSyn, and these are ones which a lot of clinicians, and in fact like there are certain websites where you can in fact go and put down your symptoms and how you are feeling in order to see whether you have a particular disease. All of them make use of a rule-based diagnosis, which is based on what is called as a classification and regression tree. So this is how you can automate rules generation. The whole process of automated rule generation is what happens within them. So that's what came down in 1984, and from there Kinlan was experimenting on making them much better, and we had programs called as iterative dichotomizers and how they would be working out. So C4.5 is a much stable release, and the one which forms as basis of all stuff which we do today, which came out in 1993. So looking from there, from 1993 till 1997, it was an age which was more of governed by support vectors, and you had an onset of adaptive learning techniques using boosting as well. But then around in 97 came down this very simple idea from Amit and Jiman, and this was about, can we create a bag of trees, which is instead of using one single decision tree, can we randomly create multiple number of decision tree. So they observed one single thing was, if you are sampling down in a very different way, then you can actually have different kind of decision rules being created over there, which will make independent trees. So if it is an independent tree and multiple of them, then can we have a democratic voting, which is gives the same importance to each of them, but you listen to everybody's decision over there. And from there came down this concept about random forest. So it was existing quite good, but in 2001 was when Bremen came up with this term, the same old Bremen from who invented CART, gave a very formal name called as random forest, and the same random forest which we are using today. So from then on, this has actually taken the community with a drive. You have lot of consumer grade devices including gaming platforms like Microsoft Kinect for Xbox, which uses them for real-time processing of your body movements when you're doing body-driven and gesture-driven gaming over there. So from there till medical diagnosis, it's in a heavy use. We will be studying a few of these scenarios, but let's start with the basics first. Now, a decision tree. Obviously, you see one particular name over there, which is tree. It does not look like the banyan tree or bamboo tree, which is just outside, but it's some sort of a tree. Now, to bring you to your very basic concepts about when you were doing programming and data structures in your early days, you had perhaps heard of something called as a binary tree, and a lot of you might have also implemented a binary search tree. So we use a similar concept over here, except for that instead of searching, it will now be looking at the left or right node, and they would be taking a decision, a yes or a no. Very much intuitive to how as humans we take decision when we are faced with a very complex scenario. So let's start with a simple problem from taxonomy. Now you might have seen redwood ants. So they are those big thick red ants which are on trees, and generally you would forbid that they don't bite you, otherwise it's seriously painful because of the formic acid they contain. Now these ants are basically of 4 types, so that's called as taxonomy, where you are going to classify which type of ant they are. Now to an unexperienced eye, if you just look at ants, they are just ants, but then they can be workers, soldiers. Soldiers are the most furious one which actually bite. There is princess, you would rarely find them. Queen, it's even more rarity to find a queen. Now if we start with this problem of these ants, and let's take 2 different typical scenarios. One of them is a classification scenario in which, given an image of the ant, I want to find out what kind of an ant it is, whether it's a worker, it's a soldier, it's a princess, or it's the queen. The other problem is, given that a picture of a ant, I want to find out what is its age. So a worker which is smaller in size, so a much aged worker might be similar in height and length to a much younger soldier or to a much younger princess. Now how do we do it? So this is about classification versus regression. Regression is when you are trying to continuously find out the age, which is a continuous variable, not a categorical one, and classification is when I want to find out which of these 4 classes it's coming up. That's a category classification problem, and that's a classification thing. So let's look into the first problem, which is about, can I find out whether it's a worker, it's a soldier, it's a princess, or it's the queen. Okay, so let's take an image, and on that image of the ant, let's see if the image, on the image I can see down reproductive organs or no. So if I don't see reproductive organs, or I would see reproductive organs. So there would be 2 of these images on which I can see, 2 of them on which I will not be able to see. This is the first level of decision which we take. The second level is, if there are no reproductive organs, then let's look at the mandibles, which are the tooth of the ant. So there might be oversized mandibles which are seriously big, they appear, that would belong to the soldier. So we go down to this part, or there might not be oversized mandibles and they would be workers. Okay. Now if they have reproductive organs, we ask a different question. We ask a question that, does it have wings or not? If it has wings, then it's a princess. If it does not have wings, then it's a queen. So basically you see that this structure represents some sort of a tree, and you are taking just yes or no decisions, which are binary decisions at each level of the tree. Now from there we come down to how do we form a decision tree. Okay. Now here what you would be typically taking is, you take down an image of the ant, say that is our random variable x. Okay, I put down that x onto the tree at the first node, so it will look into all factors around x and ask one simple question. So x might have all of these information, whether it has oversized mandibles, whether it has reproductive organs, whether it has wings or not, and you will having certain yes or no, or there may be soft variable inputs over there. Now it asks this first question. Now based on the first question, it will either get a no or it will get a yes. Eventually on the no path there will be certain samples which will travel down on the no path. Then I ask another question based on whatever information is present, and I take a yes or no. Now each of these circular points over here are called as decision nodes. This is where the decision is taken, whether to go left or right, and each of them, these square ones, are called as the leaf nodes, or this is where the decision stump rests. So if you come down to one of these, you are at one of these classification classes. So this is how the whole process goes down. Now in terms of mathematics, we can put it something in very simple terms. So say that I had a feature space in which I had two features, f1 and f2, and across this f1 and f2 I would be able to somehow draw certain boundaries over there. Now the first one is the red boundary, which corresponds to this first decision over here. Okay, now based on this I can put it down into either left or right. So I just have a line equation. I can just drop any point on the space, project it onto the line equation. I either get a positive sign or a negative sign. Based on that I will be going either to the left or the right. So based on that, if I am on the left, I am at C1 and C2, which are these two. Then I go down to the next decision, which is at f2. At f2 I would be asking another question which is based on this second feature over here, and then I can classify them into C2 or C1. Similarly I do it for C3 and C4, and this is how I can split down my whole observation space into different kind of classes with different decisions. Now the question is, how do I split them? How do I use what feature, and how will I select which value of the feature to do? So this is an iterative process which gets solved while creating this decision tree. So the first step is I need to find out what is sort of what we qualify as a split function. So is it basically a line equation which is straight line? So there can be these kind of straight lines which are aligned to an axis. So this can either be aligned to one of these orthogonal axes. For a 2D case it would just be aligned to one of these axes. See, I have a 3D problem, I can have an axis aligned plane over there. So either it's aligned to the xy plane, or it's aligned to the xz plane, or it's aligned to the yz plane. So there can be these kind of ones which are aligned to each axis. There can obviously be oblique splits as well. So this can be a y is equal to mx plus c kind of line equation, which can exist not necessarily along one of these axes, but they can exist on the 2D space as well. The other kind of thing can obviously also be a polynomial. So you can define some sort of a parabola or a curve or some sort of an ellipse function over there, and this can also be used to segregate into different ones. So you can see a typical example. For each of them they have their own beauty and merits and demerits together. So if you look at this polynomial split, you are very easily able to segregate these green class from the red, yellow and blue. So even if I am using this straight line, I can get the yellow and blue and red, but then eventually on this side of it, when I want to segregate the red from the green, I might have to use this kind of a polynomial split so that I get a perfect splitting condition coming up. Now there are pros and cons and how we do it, which we would eventually come down in the next subsequent steps. The next part is that if I am splitting, the question comes as to how do I assess that I am splitting it properly, and that's what is called as assessing the purity of a split. Now in order to assess the purity of a split, what we do is that say that I have this data which is coming down at one of my nodes or at the first node. So I have different classes over there. I can just plot down my PDF of each of these classes. So you can count down and see that this PDF perfectly matches down to 0.25, because each of them has equal number of samples coming down. Now this is for each class. So the number of samples per class divided by total number of samples present in this space. Now I can take one of these splits, say in this first condition, which is a split which is horizontally aligned over here. Now if I do that, I will be getting down a top and a bottom part. So on the top I can observe my histograms again. So I will be computing my PDF on this top over there. So there are some samples from red class, all the samples from this yellow class, and a majority of the samples from the blue class which come over there. Now I look at the bottom part. Over there I will be having samples from, there will be no samples from the yellow class, but all the other three classes are present over there. Now say I don't take this split, but I take another split which is just this vertical, which is, it can very accurately, without making any error, segregate between two classes. So you club down all the blue and the green classes together, and you are clubbing down all the yellow and the red classes together. Now typically if I ask you a question as to which one would you prefer taking, the intuitive answer would be, let's go by split 2, because at least I am able to segregate between two different classes. So my first question on the ant problem, which was just looking whether they have reproductive organs, yes or no, I could club them into soldiers and workers and into princess and the queen. So it's a similar kind of problem which it is solving over here as well. The question comes that this is a mathematical framework. I just have features and their values. So how will I say that this is a perfect one which I want to do? And that's where we use a concept called as cost function. And what this does is this assesses what is the cost associated with splitting something properly. So either the cost might go up or the cost might go down, so based on what sort of a cost function you're using. Now what we use is called as an information gain. So the concept comes as that if I have done this split, I should be having very pure classes, or my entropy should be going lower over there. So we use this particular information gain index over here, which is just a ratiometric summation over the total information which is being gained. And what you do is, typically if you look at these classes left and right, and so on the left side there will be just 2 classes, on the right there will be again be just 2 classes, and if you look at their probabilities, there is somewhere around 0.5 each of them. Now this is where the information gain happens over there, because you don't find all the other classes, you just have 2 classes out of 4 classes which have a probability of 0.5. So you obviously came down at a much better entropy over here, and an entropy which is much closer towards 0 than in the earlier case. Now from there, the question is that I have 2 problems to solve. One, what is the feature I am going to use? The next question is, which value of the feature am I going to use? Now this comes down as a joint optimization problem, and that can be solved out very easily using this simple cost function which we have. So what we do is, say that I have a k dimensional feature vector, so from x1 till xk. Okay, now for each of these I can take certain number of split points called as f1 to fn. So my x1 can range in the range of say -100 to +100. I can take n number of such, say n is 50 such random points over there. x2 might range from 0 to 1000. I will take f1 to fn, which are some random number of points only on x2, which will be in a value from 0 to 1000. My x3 might range in the value of -0.5 to +0.5. My xk might range in the value of 100 till 1 million, and I would just be taking random number of n samples from them. So it's not necessarily that the same values are taken for each vector, they will just be randomly picked up within that dynamic range. Now if we do that for each of this feature and each of these values, I will be able to design a split. So whether the feature value is greater than or less than that, and based on that split condition, I will be able to compute my information gain. Now this gives me a 2D matrix over here. So for the first feature and the first value, I get an entry. For the second value of the first feature, I get another entry. For the nth value of the first feature, I get an entry. For the second feature, I take the first value and get an entry. For the second value of the second feature, I get an entry, and similarly this keeps on repeating, and I would be able to fill up my whole matrix over here. So you see that I am drawing down different splits over there, and appropriately I am getting down an information gain which I fill within the matrix. Now out of this whole matrix, there would be one point where I would be getting the maximum value of information gain coming down, and this maximum value of information gain will be the point which gives me an optimum split. So typically this is where it's just a maximization finding within a 2D matrix, and a very simple problem. So you are solving both the problems together. So what value and which feature to use together to split in one single shot over here. Now from there we go on to the stopping criteria, which is I cannot keep on splitting forever long. So at some point of time I might end up that there is only one sample at one node. Now I don't know what to split over there, so obviously it's going to be that particular class. Now if we keep on doing that infinitely, then we would actually land up into getting down the number of nodes equal to, in the worst case scenario, the number of nodes will be equal to the total number of samples which are present over there. So say in your training you have 1 million samples, which is not so hard to imagine as such, because a 1 megapixel image would actually have 1 million points over there. So if you build a 1 megapixel image without any stopping criteria, then you would actually be ending up getting down, in the worst case scenario, 1 billion such leaf nodes which are associated with the decision. Now instead of doing that, what we do is we set a criteria that if the number of samples which come down to a node falls below a certain number, I just stop over there, or otherwise if the information gain over there is not substantial, or say the entropy is very close to 0, say the entropy is somewhere in the order of 10 power minus 3, then I would be stopping it down, which means that there are some other classes present in those samples as well, but they are negligible as compared to the majority of the class. So this can be two different criteria which we can use. So before you start splitting down a node, since you will always have to compute the entropy before split, so once you have that computed, you can use that as a stopping criteria to decide whether I want to use any splitting function further or not. So this is how we can stop down. There are obviously many other ways. So sometimes trees are created, so this depends on what kind of packages and implementations you are using. There are certain implementations which would offer you that you can grow trees up to a fixed depth only. So beyond that depth you will never be able to grow your tree any further. So there are multiple facts which play around over there. Now from there till step 4 we could use our training samples and create the whole tree. Now the question comes as, if I want to predict out of this tree, which is on the testing side where I don't have any more class labels given down to me, then what I would do. So I put down on my first mother node, which is the 0th level node, the sample. Now it will use one of the features over there which is on my split condition, and then do a yes no split. Based on that it will be traversing. So if we look typically over here, this is how it would traverse. So for this particular example it goes down to this one, then till here, then here, here, here. So these solided nodes, and as you see it going down over here, this is just the relative probability distribution across each of these nodes. So what it shows is that this is the probability of samples which flow down across these ones, and this was computed during the time of training, because here I don't have a label associated as such, so I can never compute this one. So during the time of training I can always compute this and encrypt, and you see that this is where it was not at all pure. There is a high probabilistic chance. So basically any class has a probability of getting classified as a 1/4 or 0.25. This is where it comes down to a very high probability of belonging to this red class. So this is how the whole purity comes down in the decision tree, by just doing yes no kind of questions. Now from there is the question of how do you deploy a decision tree. Now when we are speaking in terms of deploying a decision tree, the fun comes is that you have an input data space and none of them is labeled, right? Now what do I do? So during testing what I would do is, during training obviously I got down my samples over here. During testing what I do is I pick down, so I can either randomly take down from this space from where I want to test, or I can take in order, because in any case I will have to test down over all the samples present over there. So I take one sample, I pass it through over here, it does this if else if else. So if you remember your binary decision tree programming, so at each node you can obviously take a left or right traverse decision over there. So either a left traverse or a right traverse, and then based on that you end up going to another node, and on that node you again do a left traverse or a right traverse. So if it's a left traverse, you go down to the pointer which points to the left traversal to the next node over there, and you eventually at the leaf node you will have a null pointer to any further, and there would be a class probability, and this probability is actually during training whatever was the posteriori probability of each sample coming down. So that posteriori probability is the number of samples for each class which landed up on that particular node divided by the total number of samples which ended up on that node. So if it's a true classification, say for the red class, then red class will have a posteriori of 1, other will all have a 0. If it is somewhat so there might be impure classifications as well, where your red class might be 0.98 and all the other 3 classes may be 0.01, there might be 0.005 and 0.005 respectively. So you would be getting down these posteriori probabilities over here as per your Bayes theorem, and during training what happens is you actually create down the whole tree and the whole traffic passes down the whole thing. So this is the basic difference in how you would be doing it. So eventually in the subsequent ones, when we do about random forest and I discuss about certain properties of random forest, we would also be covering one simple code snippet example where we show how we are going to train this whole model. So with that I would be concluding on decision trees, and we wait for the next one on random forest. Thank you.